So in our pursuit for the perfect adder circuit, we'll first need to consider a general approach to computing so-called prefix products for a bunch of values. So we'll assume that we have an associative operation. This operation will denote just by circle. And we have some values, A1, A2, up to AN. And our goal is to compute all such products, A1 times A2, A1, A2, A3, and so on. So this associative operation means that for any x, y, and z, we have x, y times z, the same as x times yz. We'll heavily use the fact that our operation is associative, and our goal is to compute the prefix products of this whole product. We are calling this the product, but really it's more general than just multiplication of numbers. This can be multiplication of matrices or even something beyond like standard multiplication, and we'll actually use this scheme in a context which involves no multiplication of numbers or matrices. So let's denote by pi the product of the first I a's. So A1 times A2 times AI. And we'll build a circuit that simultaneously computes all these pi's from P1 through Pn. The depth of this circuit will be logarithmic on n. We'll assume, just as we did in adder, so we combined our adder out of building blocks, sigma 0 and sigma I. And here we'll assume that we have a building block, like some kind of sub-circuit, which is able to compute this operation circle. So we supply it with two things, x, y, and on the output we have the result x and y. So according to this operation, whatever it is. So let's assume that we have these building blocks, and let's see how we can build a multi-layer circuit that computes the prefix products. The inputs of this circuit are, of course, A1, A2, up to AN. These are the input nodes of our circuit. The outputs of these circuits are all these PIs. So on the first layer, we will place these sub-circuits which are able to compute our operation for all the I from 2 to n. So under A2 we'll place an element or a sub-circuit which computes A1 times A2. For A3 we'll place this element which will compute the product of A3 and A2. And we'll do so for all these columns of our scheme. On the second layer, we'll do the following. We'll take A3 and all the subsequent elements, place a computation node, a gate, this kind of generalized gate, under each of these elements, and this node would compute the product of the node which is immediately above it and the node which is 2 nodes to the left. So for the leftmost node of this layer, we'll supply just A1. For this node, we'll supply the results of this node. For this node, we'll supply the result of that one, and so on and so forth. So let's see what type of products we have computed here. So here in this node, we have the product of A2 and A3, which we had here, times A1. So here we have A1, A2, A3. In this node, we have the product of A3 times A4 and A1 times A2. So actually, at this node, we have the product of all first 4 values. At this node, for instance, we have the product of A4 and A5 multiplied by a product of A2 and A3. So here in this node, for instance, we have the product of A2 through A5. And by the way, it is highly important here that our operation is associative. So this is actually A2 times A3 in parentheses times A4 times A5. But as our operation is associative, we can forget about all these parentheses here. So we now see that on this layer, we have the products of 4 consecutive values. Now the next layer will be organized similarly. So on this layer, every node was linked to the one above it, and the one above and to the left. On this layer, every node was linked with one above, and one above and 2 to the left. Now on the next layer, every node would be linked with the one above it and 4 to the left. So here we'll have a node under this 5th column, and this node will also get this value A1 and compute the product of the output of this node and A1. Now this node will compute the product of its upper neighbor and the node that we had here. So we'll supply it with this value. This node will compute the product of the upper neighbor and this node. So now we see that, for instance, here we have the product of what things? Now, here we had a product of A4, A5, A6, and A7. And here we have a product of A2 and A3. So now here in this node, it looks like we will compute the product of all A's from A1 through A7. And on the next node, for instance, if we place a node here, we see that in this node, which is supplied with this value, will compute the product of all A's from the very first one to the 8th. And so on this layer, we'll have the products of all 8 consecutive A's. Well, up to this layer, we'll have all the products of up to 8 consecutive A's, we can say. So now, how many layers do we need so that we have all the products of up to n A's? Well, we have logarithmic number of layers. Each time we join a node on the next layer with the one immediately above it and the one which is one upper and 2 to the power of k to the left. So here we moved one step to the left. On the next layer we have moved 2 steps to the left, and so on. So we'll have a logarithmic number of layers before we are able to compute, well, actually the product of all our n A's, all our values. How many nodes would we need in such circuit? Well, on the first layer we have n-1 nodes. On the next layer we have n-2 nodes. On the next layer we have n-4 nodes, and so on. And this would add up, as we have logarithmic number of terms here in the sum, this would add up to something which is big O of n times log n. So the depth of this circuit, generalized circuit, is logarithmic in terms of the number of values for which we are computing the result. And the size of this circuit is big O of n log n. So now we'll employ this kind of scheme by carefully defining what our operation is to compute simultaneously or almost simultaneously all the carry bits that we can have while adding two binary numbers. And thus we'll get rid of our super long chain in the adder. So now we will go on with carry look ahead adder.